Hello, physicists. Today we are going to be starting a brand new unit. This is Unit 5, which is on electric circuits, and Lesson 5.1 here, we're going to be looking at electric current and Ohm's law. So for this lesson, we are going to be focusing on the big idea for this unit, which is energy is found in different forms, is conserved, and has the ability to do work. So there's a few terms there that we're familiar with, like energy, work, and conservation. We're going to apply that to electricity though, and we are going to be looking at current, voltage, and resistance, and we're going to be tying those things together with something called Ohm's law. So before we can start talking about electrical currents, we might ask, first of all, what is electricity? And when most people are asked this question, they'll answer by saying something like, it's an electrical current. And that's not wrong, but in physics, we obviously need a clearer and better explanation for what electricity is. So let's take apart that first that response there. We recognize that current infers that something is flowing. So if we say electricity is an electrical current, current means that something is flowing. So we would ask, well, when we're talking about electricity, what is flowing? I mean, if we're talking about water, the water is what's flowing. So if we're talking about electricity, what's flowing? And now we need to go back and we're going to talk a little bit about convention. So there's some conventions that we use when we're talking about electrical currents, and there's also the reality of what's happening. And here's the reason why. When Benjamin Franklin was experimenting with electricity, and this is before we knew anything about the structure of atoms, he suggested that positive charges were responsible for the electrical current and that they flowed from positive to negative. So let's draw a very simple current. So we're going to have a cell or battery here, and we're going to have a negative and a positive terminal. We're going to have a wire here that's connecting the terminals. This here is a resistor, okay? And what Franklin thought was that there was a bunch of positive charges and that they were moving in this direction from positive to negative, okay? Not a bad guess. Again, we didn't know anything about the structure of atoms at the time. However, now that we do know what an atom looks like, and you'll all be familiar, I'm sure, with this model of the atom. So we've got a nucleus here of protons and neutrons, and around those we've got our orbital shells, and that's where our electrons are hanging out. So this is where our electrons are hanging out. Now, we can see that the electrons, so these negative electrons, are not only around the outside, they're much smaller and much lighter than those protons that are inside and much more likely to move. So it turns out actually that what's happening if we look at an electric circuit, it is not the positive charges that are moving. But again, we'll just draw the same circuit, a little resistor down there. It's not the positive charges that are moving, it's these negative charges that are moving, and they are going from negative to positive, okay? And even knowing that, there's a lot of stuff that we have to explain, but this is the first step in understanding what we're talking about when we say an electrical current. So current, again, is something flowing, and now we have an appreciation that what's flowing is actually these electrons, which are carrying a negative charge. So we can come back now and we can say, well, electrons moving in a certain direction is an electrical current, okay? And electrical current is denoted by the letter I, the capital letter I is for electrical current, and the reason for that is we're going to talk about coulombs in a second, and so they didn't want us to be confused with coulombs and current. So electrical current got the letter I, whereas coulombs got C. Okay, so now that we know that electricity is this flow of electrons in a certain direction, the first thing we might like to ask, the first practical question we might want to ask is, well, how fast is this current flowing? Okay, and to measure that, we're going to need to set up a boundary across which we can measure the flow of electrons. So what are we talking about here? And again, I keep drawing this cell, what we call a cell or a battery, and we're going to come back to the importance of that. We're just going to focus right now on the movement of the electrons. And we'll need a resistor in here somewhere to make a circuit. Okay, So we just said we've got these electrons. They're flowing around. Actually, for right now, let's just keep electrons as little negative symbols. So we've got electrons and they're flowing around and they're going in this direction. So what we would need to do if we wanted to see, well, how fast are these things flowing? We'd have to set up a boundary. So we've got a boundary here. And we would want to know, well, okay, how many of these electrons are passing the boundary per second? So what we would like to know is, well, our current could be how many of these charges or how many of these electrons, and we show electrons like this, are going past our boundary every second. So this would be one way to figure out our current. Now, if we actually try this in practice, we quickly see that our numbers become unwieldy, and that's because electrons are so small. And there's no general agreement on this, but an approximation of how big the diameter of an electron is 1.0 times 10 to the negative 18 meters. So the estimates are all around this size, extremely small. So if we're going to try to count individual electrons, we're going to have trouble because we're going to have so many. Even in our finest wire, we're going to have so many electrons flowing. So to make things more manageable, we group our charges or our electrons into bags of electrons, and these bags of electrons are called coulombs. So we can draw, what is a bag of electrons going to look like for us? Let's just say, here's our bag of electrons. So now we've taken those electrons and we've put them into this bag. And we'll call each bag is going to be 1 coulomb. Okay, and so coulombs are named after the French physicist Charles Augustin de Coulomb, and 1 coulomb is equivalent to the charge of 6.24 times 10 to the 18 electrons. Now, how the heck did we come up with this number? Where is that number coming from? Well, the fundamental charge, and again, we call charge is Q, so this is important for us to know. Charge is Q. The fundamental charge, or the charge of a single electron, so this is the smallest charge possible that a particle can carry, is negative 1.6 times 10 to the negative 19. So they said, well, what's 1 coulomb going to be? 1 coulomb is going to be 1 divided by the number of, or 1 divided by the fundamental charge, and that means that we have 6.24 times 10 to the 18 electrons, that's the number of electrons in a 1 coulomb charge. So 1 coulomb is equivalent to the amount of charge that is carried by 6.24 times 10 to the 18 electrons. Okay, so let's note here that when we do this, our coulombs cancel out, and so our coulomb is dimensionless. And in chemistry, we have something similar called the mole, and the mole actually serves a similar purpose. So just like in chemistry, the mole is saying how many atoms are in a bulk sample of a substance, and we have Avogadro's number, which is 6.022 times 10 to the 23rd. Our coulomb is doing the same thing. We're bagging up these electrons and we're grouping them into a manageable charge so that we're not counting individual electrons, just like with the mole, we're not having to count individual atoms, okay? So now that we've got this new way of counting charge, and we said instead of counting the fundamental charges going through, we're going to count coulombs instead, we can go back and we can now measure our flow of electricity as our charge per second, and our charge is now going to be in coulombs. And this is going to give us coulombs per second, and coulombs per second is equivalent to the amp. So 1 amp is going to be 1 coulomb per second, and let's redraw now one more time our circuit. Here's our negative terminal, our positive terminal, and instead of saying, okay, we're going to have a look at how many electrons are coming around, we're going to now be looking at our bags of electrons. So we're going to count how many of these bags go by our boundary in a second. So again, we're still going to have the boundary. and we're going to say how many of these 1 Coulomb bags are passing that boundary in a second. So this is what we're talking about when we talk about current. It's the amount of charge per second that's going through a current. So that's our first thing. So we've got a couple of equations here. We've got our current is equal to our charge over our time, and we've also got this number of electrons is equal to our coulombs over the fundamental charge. So those are two handy equations for us. So the next thing that we might like to know is, well, we keep saying that we've got these charges moving, but we might like to know what is causing our charges to move. And the answer is the potential difference across a cell or a battery. So now we're going to focus on that cell that I keep drawing, which is related to the electric potential energy. So we're familiar with potential energy in terms of gravity around planets, but what do we mean when we say electric potential energy? Okay, well, we're actually going to use the gravitational fields around a planet as sort of an analogy to look at what's going on in a battery with electric currents. And we're going to have a look at what does it mean, potential difference across a battery or cell. So if we look at this thing, if we've got we got a circuit here with no battery, we've definitely got electrons in here, but they're not going to flow. So a wire sitting by itself is not going to be any problem to us. We're going to be able to handle that wire. It's not a problem. But if we've got an energy source, a cell or a battery hooked up, and the convention is the negative sign is going to be the short line, or the negative terminal is the short line, the positive terminal is the long line. Now we are getting a flow of electrons once we put this cell or battery in the circuit. So what's actually happening here? Well, if we want to talk about the potential difference across this battery, let's think about what we mean when we actually say potential difference. So here, let's go to our example of the gravitational field. So here we have a gravitational field. This is the Earth, and there's the surface of the Earth, right? And so we can say that we know that this, we're going to have a uniform gravitational field when we're close to the Earth. And we know that that's actually going to get weaker as we go further away. But for this case where we're close to Earth, we can say that this gravitational field is, for all intents and purposes, uniform. And we're going to put an object on the surface of the Earth. And we said to get this object to move against that gravitational field, so to take that object from position 1 down there to position 2 up here, we are going to need to do some amount of work. So we're going to have to do work against the gravitational field, and that means that we are going to have a change in potential energy from point 1 down here to point 2 up here. Okay, so when we have a change in potential energy, we know that we're actually talking about mgh final minus mgh initial. All right, so we are going to have to do some work against the gravitational field to move this object. And what we're interested in is we're not so much interested at what the potential energy is at any point. We're interested in, to move this thing a certain distance, how much energy is it going to take us? So if we redrew this, we're not really so much interested in whether or not this thing is on the surface of the Earth or whether it's already hovering in the air and we move it when it's already in the air. What we're interested in is to go from one distance to a second distance. How much energy is that going to take us? Okay, so to move against this field a certain distance, how much energy is required of us? Okay, and so we can see if we look at something like a body of water. So let's have a completely level body of water. You aren't going to move, this water isn't going to move if it is completely level. It's got no reason to move in one direction or the other. However, as soon as you introduce a change in height, now you've set up the conditions for the water to flow, right? So now the water is going to flow. If it's just sitting here and there's no potential difference, it's not going to flow. But as soon as you increase height, you are enabling this water to flow. So a change in height causes water to flow. So we could also say a potential difference is required for water to flow. And we're actually going to see that this is no different than electricity. And to really understand how this here, our potential difference is set up by a change in height, but with our battery, we're going to get a potential difference, and we need to sort of understand a little bit about how a battery is working and a little bit about electric fields to understand why we're getting a potential difference in a battery. But let's look at a simple battery, a dry cell battery that everyone should be familiar with. These are the components. You're going to have an anode made of one type of metal, and that is going to house your negative charge. So this is your negative terminal. And you're going to have a cathode, which is got positive charges, and you're going to have an electrolyte. So in this case, we've got a paste of manganese oxide, and what this is doing is it's actually stimulating a reaction, and the reaction that this electrolyte is stimulating is called a redox reaction or an oxidation reduction reaction. And this is in your Chemistry 12 curriculum. So you'll do a lot about redox reactions in Chemistry 12 and then again at university. But all this is really a reduction is you're gaining electrons, and an oxidation is you are losing electrons. So you're being reduced by negative charge, or you're being oxidized by the loss of negative charge. So we're getting this redox reaction thanks to our electrolyte, and we're getting this buildup of negative charges at the anode. Okay, now when we get a buildup of like charges, these things don't really want to be next to one another. They don't want to be crammed next to one another, but we keep getting this buildup of these negative charges. Okay, and the problem is the anode and the cathode aren't in contact, so these negative charges, they've got nowhere to go. But as soon as we put a wire connecting our negative terminal, and we may have a resistor, we may have an LED light or something here that's giving off energy, something that we want to power. As soon as we make this connection between our negative terminal and our positive terminal, we've just given these things an opportunity to flow. Now we've given them a path to get away from each other. So essentially, when we do that, before we connect them, we've got all of this potential for these things to move, but they've got nowhere to move. When we make that connection, now we go from potential to kinetic. These things start moving, and we're going to have negative charges start moving towards the positive terminal. Okay? So this is great. This again explains to us why we're moving, but it doesn't really explain the potential difference aspect. And for that, we're going to take a little detour into Physics 12 here for a second, and we're going to talk about electric fields. So this is where our analogy with the gravitational field really becomes useful. So if we have two charged plates, so this one's going to be negative, and this one's going to be positive, and we are setting up an electric field between these things. So our electric field, again, convention is that our electric field is going from positive to negative. And let's say I'm going to have some really unrealistic numbers, but they're just going to be nice and easy for us to work with. So E here is not energy. This is electric field. Okay, and let's say we've got an electric field of 5 newtons per coulomb. Okay, and now what we're going to do is we are going to drop a charge in here. And we'll see that charge at a couple of different locations. So let's say, again, to keep things easy, we'll say we've got a 1 coulomb charge here, and we've got a 1 coulomb charge here, and we're going to have 2 meters in between them. Now, obviously, if we're talking about a 1 coulomb charge, 2 meters is kind of a ridiculous number to have for your distance, but we're just going to use it again because it's easy numbers to work with. So if we have a 1 coulomb charge, then we might like to know, well, what is the force being produced by this electric field? And so we can easily figure this out. We can say that our force produced by our electric field is going to equal our electric field, which is in newtons per coulomb, times the charge that we've got, and so this is going to equal 5 newtons per coulomb times 1 coulomb, and that means that our electric force, or our force due to our electric field, is going to be 5 newtons. Okay, so now we can say, well, if we know we've got a 5 Newton force acting in this direction, acting in the direction of this magnetic field, how much work is it going to take for us to move our particle from here to here? Okay, so we can say, well, we know we've got a force of 5 newtons, and we know that work is equal to our force times our displacement, and so we are going to get 5 newtons times that 2 meters, and we are going to get our work is equal to 10 joules. Now, what we're interested in, and I've made this just 1 coulomb again, and you'll see that that's really easy because what we might like to know is how many joules will it take to move that coulomb, the 2 meters. So we're interested in joules per coulomb. So that is actually voltage. Voltage is our joules per coulomb. So again, it's the exact same thing. We are moving something against a field, a field of force here. In this case, it's an electric field. Up here, it was a gravitational field, but we're moving an object within a field, and that means that we are changing its energy. Okay, so this is why we're getting a change in potential energy, or we have a potential difference. A battery is creating this potential difference because it's setting up this situation where we've got a bunch of negative charges here, and we've got positive charges here. And so there's a potential difference here. These charges want to be down with the positive ones, and we make that connection, and then they can finally start moving. So just like we need just like we need a change in height for water to flow, we need a change in electric potential difference for electrons to flow, or for charge to flow, okay? And just to finish this off, once you get enough negative charges over here, once you have an equal number of negative charges on this side as on that side, you're going to stop the flow. This is what happens when our battery dies, right? Because once you've got the same amount of negative charge here as you've got here, there's no more reason for these things to flow, right? There's no more benefit of them coming over to this side. So that's when our battery dies. And so when those things start to flow, then we get, well, our light bulb switches off. Okay? So really important definition here. Voltage is the amount of work required to move a charge from one location to another in an electric field. That's what we just looked at here. Just like you need a difference in height for water to flow, you need an electric potential difference for charges to flow. and it's the battery that creates this potential difference. Okay, so that's the most complex part of what we're going to talk about. We'll finish off by talking about resistance here. So resistance, which is denoted with R, and sorry, did we say voltage is V? Hopefully somewhere. Okay, we'll make sure that we say voltage is V. Okay, and resistance is R. Resistance is just how much the material carrying the charge reduces the electric current, and it is measured in ohms. So the resistance can be due to the material that your current is made out of. So it could be due to the material like your wire that your circuit is made out of, or it can be due to an actual resistor that looks like that you put in your circuit. And you can have a resistance across this resistor, and that's going to be measured in ohms. So when you put in a resistor or you change the material, you reduce the electric current. So you can reduce the electric current with a resistor. So now that we know about voltage, we know about current, and we know about resistance, we can put these things together in something called Ohm's law, which describes the relationship between them. So Ohm's law is commonly written as voltage equals current times resistance, and we can also flip it to say that current is equal to voltage over resistance, and it might be a little bit easier to think about it in this second way when we go down and talk about this analogy here. Okay, but we can also look at this mechanically and we can say, well, what are we talking about here if we're looking at current equals voltage over resistance? Well, we're saying that our current is directly proportional to our voltage. So if our resistance stays the same, if our voltage increases, then our current is going to increase. And we can also look at it in terms of resistance, and we say, well, if we keep our voltage the same and resistance increases, then our current is going to increase. Okay, so obviously what this is saying is if you change the potential difference here, so if for voltage, if you increase the potential difference of your voltage, you're going to cause a faster flow of electrons. Okay, so that's the way to think about it. But we can also think about it in this really neat plumbing analogy, and this is something that's really popular in most introductory physics courses. They do some variation of this plumbing analogy. So we've got a pipe here, and the pipe has a cover on it. And behind that cover, it's holding in a bunch of water. And that water is at some pressure in the pipe. Here's our pipe. Okay, so we're saying our pressure is similar to our voltage. Our pressure is what's creating our potential energy. So this pressure buildup is we've got this stored energy that's able to do work. And if we flip open the lid on this thing, what's going to happen? Well, we're going to get a bunch of water pouring out of here really quickly. Okay, and if we increase the pressure, if we jack up the pressure in our pipe here, our water is going to come out even faster. Okay, so that brings us to this proportionality here. If we increase that voltage, or in this case, if we're increasing that pressure, we're going to increase the flow, right? Now, if we do something like this, we make a bend in the pipe like this, where we reduce its circumference. And now we do the same thing. This is still our pressure. And we can even have the same pressure that we had here in this first situation. And we can have our water here too. But now, when we open that lid, we're going to have a much slower flow because we're being restricted. It doesn't matter that this opens up again here. This choke point here, or this bottleneck, is really our determining factor. So it doesn't matter if this comes back up and opens up again. This is our resistance. And this is going to determine the flow of those, flow of the water, or in our current, it's going to determine the flow of our charge. So if we put this resistor in here, we're going to get a much lower flow. So what we've done here, let's be very clear. We have decreased the circumference of the pipe, which has increased the resistance. And if we increase the resistance, we get a reduced flow. Again, we come back up here, we've got this, this relationship where it's inverse. So we say if we increase the resistance, here we're going to decrease our flow. Let's get rid of that area. Increase resistance, we're going to decrease our flow. Okay, so that wraps us up for our first lesson here for electric current. We talked about voltage and we talked about Ohm's law. And the reason that I wanted to go through that information the way that I did with those analogies is because it's actually, a lot of people just jump straight into talking about Ohm's law and talking about circuits, and we're never really sure why is the charge moving, or what is the actual flow? What are we talking about here? What's flowing? So hopefully now you have a pretty clear understanding, and we'll just whip back through here and summarize really quickly. So we said electricity is going to be an electrical current, which means that something is flowing. And we said, well, what's flowing? Initially, we thought that it was the positive charge, but we actually have found out based on our knowledge of the atom that it's actually the negative charge that is flowing, and we're going from the negative terminal to the positive terminal, and we saw why when we looked at the battery. And so we said that movement of charges is our electrical current, which we call I, and it's measured in amps. And so how do we figure out amps? Well, we've got to figure out how fast is our charge flowing. We said we don't want to do that looking at individual electrons. It's much easier to use these coulombs, which are bags of electrons, we can think of them as, or grouped charges, and 1 coulomb being the amount of charge that is in 6.24 times 10 to the 18 electrons. And hopefully let's appreciate that this is an absolute value here, because it wouldn't make sense for us to talk about negative electrons. Okay, and so now that we've got that, we can say our current is equal to our charge over time, our charge per time. So we're looking now at these coulombs going past our boundary per second. And then we said, well, what's actually causing those coulombs to flow? What's causing our charge to flow? And we said, well, it's the potential difference across our battery. And we compared that to the gravitational field, and we saw that moving something in a gravitational field is very similar to moving a charge in an electric field. And the potential difference is set up by this reaction where we're getting a whole bunch of negative electrons, a negative charge at the anode, and they want to go to the positive cathode. And when we connect the positive and the negative terminal, then we're enabling that potential turns into an actual kinetic flow of charge. So the potential difference sets us up for us to be able to move that charge. And so we said, wrap that up by saying that voltage is the amount of work required to move a charge from one location to another in an electric field, and we need that for our charge to flow. Finally, we said our resistance is just how much the material carrying the charge reduces the electric current, or how much a resistor is able to reduce the current. And we put these things together using Ohm's law and our handy plumbing analogy here. Okay, I'm going to stop the video here. I'm going to do a second video where we go through a couple of the practice exercises. There's not a lot of practice exercises here because when we do our next lesson, which is on power, we're going to have a homework assignment after that, which includes our Ohm's law and our current, and we're going to talk about power as well in that homework assignment. So we'll have a pretty light lesson for this one.